Okay, so this is a little recap question from last time. I'd like you to sort the access modifiers in order of least to most permissive. So the things which are strict and allow you to do the least amount of stuff should come first, and the things that are less strict should come last. And the order should be private, package, protected, public. So remember last time I had that little grid and I labeled one of them as surprising. That is that protected is less protected than package. So just remember that that's the order. I think it's just a badly named keyword. Protected means that everything in your package can see it and any subclasses of yours, which is what we're going to cover next week. Okay, next question. Have a go at this one. Okay, so encapsulation means hiding internal state. So we saw that last time with student and age, and we wanted to make age private so that people couldn't set my age to -1. Encapsulation also means packaging behavior with state. So that means that we can look at our particular implementation and see that all of the ways that we can interact with that state are kind of all grouped together. Encapsulation does not mean separating general concepts from specific ones. Sorry, that seems to have been truncated. That's what abstraction is, and I'm going to cover that later in the course. And encapsulation has got nothing at all to do with immutability. Immutability is like an entirely separate concept to encapsulation. You can have immutable things with no encapsulation because you can use final, for example. Okay, so today's lecture is about pointers, references, and memory. And you may sit here today thinking, why are we having to learn all of this low-level detail about memory and bytes and how things are laid out? And the reason why this is here is that, for me at least, the thinking about how the machine actually does things helped me understand what was going on when somebody said, oh, you can update this because it's a reference, and you can't update this because it's a value, and this is a calling convention, and all this kind of stuff. So what we're going to do is we're going to go sort of down the layers, and we're going to look at the way a machine works a bit, but with the intention of meaning that that makes it easier for you to understand what's going on when you're writing the Java code as we go back to it later in the course. So by the end of the lecture, you should know what a call stack and a heap is. And also, it's a particular kind of heap. And I want you to also know the difference between pointers and Java references. So I've mentioned the word reference quite a few times. By the end of this lecture, you should know really what that means. All right, so when I was practicing this lecture yesterday and I was going through the slides, I realized that the handout I sent to the printers omitted about 24 slides, which I actually needed today. I put them on the website, and I will get the department to do a print run of them, so I'll have physical copies for you to take away. But apologies, you'll just have to follow along on the slides for the moment, but you've got the video to refer back to as well. I'll put that online. So here is the additional magic handout that none of you have. I will get printed copies available for you. So this picture here is a schematic diagram of what the computer's memory looks like for storing data. And conventionally, when we draw this thing, we have cells, and each cell is a byte of data. So remember, a byte is 8 bits, so it can store the number 0 to 255. So there's my byte. And this machine has 4 bytes in a row in this diagram going down the page. So machines normally group bytes into a larger chunk of something. It's called a word, because messing around with 1 byte at a time is really quite difficult. You can't do much with it. So we instead deal with chunks of byte at a time. So this is a 32-bit architecture machine. So we know it's 32 bits because there are 4 bytes per word. That's what the row is. The numbers on the left-hand side of each row is the address of that row. So if I tell the machine I want to read the value in memory at address 120, that means tell me what values are stored in these 4 cells here in the 120 row. We normally write our addresses in hexadecimal. I'm going to write them in decimal today so that I don't get confused about what numbers are. Finally, there are 2 arrows here, one going down and one going up. So your program has 2 basic sort of areas of allocation, the call stack, which we normally would draw as going down the page, and a heap, which we would normally draw as going up the page. And these 2 things sort of grow together, and we just make sure there's enough space between them that they don't actually collide. And what I'm going to do is explain what happens on the call stack and the heap now for the rest of this lecture. So this is an example in C and C++. I'm going to come back and do a Java example later, but one of the nice things about C is that you really know exactly what it's going to do in memory. And one of the really bad things about C is you know exactly what it's going to do in memory. So this is going to be the example. I will explain all of the syntax. On the left-hand side now, you can see a program. The numbers 1 through 7 are just line numbers, so I can refer to things. They're not part of the code. The little double angle thing is the instruction pointer. So this is the line of code that the computer is going to execute next. So we're going to execute the code f of 4. We're going to call the function f4. Now, in order to execute that function, we have to allocate some stuff in memory. We allocate something called a stack frame, and it contains at least this stuff. It also contains some more stuff, but it contains at least this stuff. The first thing it contains the integer 4, right, which is the value on line 7 that we called the function with. So you can see in memory, on this row 100 here, I've allocated the integer 4 by writing the byte 4 into one of these cells and then 0 into all the others, because the integer 4 is just the number 4. It's got nothing else in the higher ones. On the right-hand side of the diagram now, I've labeled rows with a sort of a marker that's only for my benefit of what that row represents to the programmer. So the row address 100 is the variable x. And then I've allocated 4 more rows for C, L, and I, which are the variables I'm going to use in my function call, C, L, and I. Now, C is a char, and so chars are 8 bits in C, so it's going to take 1 row, because we never go like less than a row. A long in C is 64 bits, so it needs 2 rows, because it's got 8 bytes in it. And then an int in this version of C is 32 bits, so that's just 1 row of the program. So that's the space that I've had to allocate for it. This is my stack frame. It's stack frames. Every single time you call a function, you have a stack frame, which is where the function holds the state of all its local variables. So now as we execute the function, we start filling things in. So the first thing we see is that we want to store the letter A in memory. Now, you can't store the letter A in memory because your memory is 1s and 0s and can only store numbers. So what you do is you store a number which the whole world understands is the letter A. And that number is 97. How many people have heard of ASCII? Yeah, okay. ASCII is 97 for A. How many people have heard of Unicode? Unicode is what happened when people who were building computers realized that there were more letters in the world than just those that were in ASCII, and they had to make more space for them. We're just going to think about ASCII today, so that's just 8-bit characters. So we allocate the number 97, but when we look at that number through the lens of, I want this to be a character, then we'll think that it's a letter A, right? So if I tell Java, for example, to print the contents of memory at this row, and I've told Java it's characters, then Java will read 97 and print A. So then I want to put the number 1234 into this long. Now 1234 is bigger than 1 byte, so it's going to take up 2 cells in my space rather than 1. And so I need to write the number 210 in the first cell and then 4 in the second one. And that's just if you wrote out 1, 2, 3, 4 in binary and chopped them into chunks, those would be the numbers you'd need to write. And remember, because L is 64 bits, it needs 2 rows of this space. So we've taken up more space on the stack in order to store that value potentially. And then finally, we allocate the int 10, so that gets its own row on the right-hand side there. So conceptually, what we've done is we've just stored these things that are sort of like in the stack frame. I'm going slowly here because I'm going to add lots of arrows in a minute, and I don't want you to all start screaming. Arrows. So, C and C++ have a thing called a pointer. And a pointer is an arrow that indicates that you should go and look somewhere else for the value that's stored here. So here is my stack frame on the right-hand side, and I've stored 3 ints in it, I, J, K, with the numbers 1, 2, and 3. You can see those labeled on the right. And then I've got these 2 things, P and Q. And in the program, you can see that P is something called ampersand I. That means the address of I. And Q is ampersand K, the address of K. So what does that mean? Well, the address of I is 100. It's the number in memory where I've stored the 1. And the address of K, is 108. That's the place in memory where I've stored the number 3. And since P and Q are pointers, they are just those addresses get stored in memory at those points. So you can see here on the right-hand side, I've stored 100 in row 112, and I've stored 108 in row 116. Those are the addresses of the things they want to point to. And to make it easier for us to remember what this means, I've drawn some little hooked arrows around to show where they point. So P line, which is the address 100, points to I, which is therefore a little arrow that goes up to the top, and Q points to K, which is the arrow that goes around there. So a pointer is a really simple thing, right? It's just a value in memory, just like an int or a char or anything else. But rather than that value being some data, that value is an address to say, like, go somewhere else. It's like if I ask you a question and you say, ask him, right? So, and you can have chains of pointers. You could tell me to go somewhere else, and so on and so on. So there's nothing really sort of magic about pointers. They're just a value in memory that you can look at and say, oh, I should go somewhere else. And the terminology we use is indirection. So we say, I want to take the value. I shouldn't have changed slide then. I want to look at that address, and I want to follow the arrow. And that's called indirection. I just follow the link, and I go to the next place. So pointers are a very, very simple concept, but that doesn't mean you can't do very, very complicated things with them. So one of the complicated things I can do with a pointer is I can do arithmetic on it. So I could say that this new pointer, R, on line 7 of this program, is another pointer, which is 1 plus P. And what's P? Well, P is an address to something else, so I want to move like one place further down the address space to find that. So let me just make that clear. P points to 100, and so I want to do like one more than P, so I'm going to jump one row down, and therefore R is going to point to 104. All right, the compiler knows that P is pointing to ints. It knows that ints are taking one row, so it will increment the pointer by the right amount. If I was pointing to a long, then it would jump it by 2 rows. So like somehow magical stuff is happening all of a sudden. But the simple idea is that like P is an address, it points to something. I add 1 to it, it points to the next one.
So if the address is 32 bits, wouldn't that mean that the amount of cells we have would be limited to 4 billion something?
Yes. So on a modern, let me just repeat the question for the video. So if your address is only 32 bits, then the total number of cells you can have is limited to like 4 billion, right? Because you can only address those numbers. And so this creates a problem on a modern machine because 4 billion is sort of like, it's a few gig. It's not a massive amount of RAM. And so one of the reasons why we've switched to 64-bit architectures is to make it much easier for an operating system to give us access to more of that space. Before we switched to 64-bit, there were lots of tricks going on to make that work. But in general, one reason for switching to 64-bit machines was to make it easy to address that extra space. So we can do arithmetic on pointers based on their size. And this star means dereference. It means indirect down the pointer. So if I write L equals star R, it means look at the address held in R, follow the arrow, and get the value back. So R contains 104. I follow the arrow to row 104, and I get back the value 2. So pointers are really like small, simple things, and that was really good when people were writing C because computers were small, simple things, and we had to make the language simple too. You could do arithmetic on it. It lets you solve all sorts of problems, but there's nothing in the compiler that stops you making a mistake. So for example, I can say that M is Q plus 1, and what is Q? Well, Q is this, this address here pointing to 108. If I increment Q by 1, I get something that points to 112. I've decided that it's an integer, but it's not an integer. It's an address in memory. So this int m actually is the value 100. I've never put an integer of 100 anywhere in my program. I've just used my pointers to look at some point of memory and go, hey, interpret this as an entirely different data type. And craziness has happened. So when you hear about buffer overflow attacks or out of range errors or piles and piles of security vulnerabilities in C programs, many of them arise from the fact that it's possible to trick a pointer to point to something that it shouldn't point to and then manipulate the data there and get something bad to happen with the program. Okay, so that was pointers. Now, we put our pointers on the stack, right? So remember, stacks are coming down from the top. And so all of our pointers are up here. We've just sort of allocated stuff within the stack frame of our function. Now, there's another thing called the heap. And the reason that they're called stack and heap, I don't know why. But one reason why they could be called stack and heap is when you build a stack, you pile things up neatly. So every time I call a function, I allocate another stack frame on top of the previous one, and I make a nice, neat stack of them. The heap, you just chuck stuff in there and just leave it there. And the times at which that gets reclaimed back and made available is entirely unorganized. There's no system to it. So if you're the kind of person who piles your laundry up nicely and you know what you're going to wear next, there's your stack, and then you take your clothes off at the end of the day and throw them in a heap. Who knows when they're going to get picked up? That's your heap of stuff. So heaps are down the bottom, stacks are at the top. And in C++, you can choose whether you want to allocate on the stack or the heap. So this program here on line 2, I've said I want a new array containing A, B, and this 0 character. And that says to C++, I want it on the heap. So it goes all the way down to the other end of memory, finds a space, and it says I'm going to store A, B, and null for you on the heap. And then C is just a pointer to that. So again, C just contains the address. It's nothing magic. It just contains the address to something on the heap instead of something on the stack. And then I can just make another pointer that points to the same thing. So you might say, well, what's the difference? Why would I care whether I've drawn one at the top and one at the bottom? And the difference is that items on the stack exist only for the duration of your function call. Items on the heap exist until they're deleted. Right? So imagine in Java, you wrote a program that was going to show like a GUI, and you wanted a function which created the main window. If you allocated the object for that main window on the stack, then as soon as your function exits, your window disappears. Right? But what you actually want to do is you want to create this thing and then have it exist for the whole lifetime of your program, even though the function has returned. So that has to go on the heap. So stack means it's nice and organized, but it only exists for the lifetime of the function. Heap means it's a pile of old stuff, but because it's a pile of old stuff, you can treat the lifetime of those things however you want to do so. Has anyone ever heard of a memory leak? Yeah, what's a memory leak?
When something which you give memory to is finished, but then never returns that memory back, and thus you've lost memory forever.
Yes. And so a memory leak is when I allocate something on the heap, like this array, and then I forget to free it. I forget to release that memory. So if I lose C, or I lose P, for example, then I've got no way of referring to that again. That memory is lost to me forever, and so my program just uses more and more over time, and eventually it crashes. I'm sure you've all seen a C program do that from time to time as well. So a memory leak is where you allocate some memory on the heap, and then you forget to free it again later. Okay. I'm now going back to the original slide, so you can now start following along again. This is a Java example of how the stack is used. So I've told you that the stack is very organized and every function gets one. What I want to show you now is how that happens and why that's valuable. And the main reason this is valuable is because we want to be able to do recursive calls to functions. So I've got my instruction pointer on the right-hand side again. I'm going to execute this sum function. And so the stack frame for a particular function now, I'm going to delimit stack frames with this heavy black line. So everything either side of a line is a different stack frame. And so my stack frame needs to contain space for all the local variables in my function. So I've allocated this S here, which is going to hold a value later. And now I'm going to execute this call. So this says the value in S should be the result of what happens when you execute sum of 3. And we don't know what that is yet. And so the instruction pointer, the compiler says, well, I'm going to need to execute another function. I need some more state. I need a new stack frame. So we allocate a new stack frame, which we're going to use to get the result of sum of 3. And if you skip the first row for the moment, you can see the second row says arg1 has the value 3 in it. So this is a row in the stack, which the function which I'm calling will use to know what argument it's supposed to compute it on, right? When I execute sum here that's defined on line 6, it's taking some n, but what is n? So the stack frame contains n, which is currently known as arg1, and that's the value 3. The line above it, this thing that says return, that's the return pointer. So that says to the compiler, once you've finished executing this function, you should go to wherever this address is and start executing the code there instead. So it's like, how do I back out of this recursive call? Well, how do I know where to go? And you'll see me use those a little bit later as I demo this through. So we start building our stack frame, and then we go over to the function, and we say, right, we need to finish off this stack frame. There's more stuff to go in here. We're going to need an M and an R, because we know we need those variables. So we allocate space for those, and then our frame is completed, and we're ready to execute code. The code says, is n equal to 0? And now you know what n is, because n is in the stack frame. It's labeled with n. It's got the number 3 in it. So n is not equal to 0. So we're going to jump over here. And we're going to say, right, I now need to know m. And m is the value of n minus 1. Oh, sorry, sum n minus 1. So I allocate a new stack frame. So what I'm going to have to do is I'm going to have to call sum again. This is a recursive call. And the recursive call this time has the argument of n minus 1, which is 2. So I write 2 into my arg1. And then my return pointer is 10. So why is my return pointer 10? Let's see if anyone's managed to follow so far. Yeah. Why is my return pointer 10? Yeah, because I want to go back to line 10 after I've executed this function, right? I'm on line 10 at the moment. I want to call sum. And when I've finished executing sum, I want to come back to that line and carry on executing code. So I write 10 for my return pointer. Then we go, then my execution goes back to executing sum. But now I'm in a slightly different world because n is now 2 rather than 3. So I now need to work out what m is again. And m is the sum of n minus 1. So now you can see I've allocated another stack frame. The argument is 1, and the return pointer is still 10, because I'm going to go back to line 10 again this time. I'm not going anywhere else, but I've just sort of come around the loop. And I'm going to execute that. And I need m again. This time, I'm calling sum of 0, and my return pointer is 10. And now I'm going to execute my code. So this time, something different is going to happen. So n is equal to 0. So I want to return. So in order to execute the return function, I need to know where to jump to actually execute the code that I'm returning from. And fortunately for me, I put that in my stack frame. That's the return address. So I know that when I execute return, I'm going to have to jump to line 10. And I also know that when I return, I have to return the value 0. So that's going to go into the thing that wanted the result on line 10, right? So here we go. So return the value 0, and then execute instruction 10. So the processor just keeps moving forward, right? Even though our program is now sort of unwinding up the call stack, the computer doesn't know anything about that. It just carries on like jumping its instruction pointer around. So it's just jumped it to line 10, but it's unwound the stack frame in doing so. So now like the context is different. We're now in this sum1 world, and we know now that m is 0. And so we now know that r is 0 plus 1, which is 1. So I store that in my stack frame. And then I need to return it. So return r, that's the value 1. And then I have to execute instruction 10, because that's the return address that's stored in my stack frame. And then it unwinds again. Then I know that m is 1, and 1 plus 2 is 3. So I have to return 3 and execute 10. And now I know that m is 3, and 3 plus 3 is 6. So I have to return the value 6. And then I have to execute instruction 2. So all the previous times that I came out of sum, I went to instruction 10, because they were like unwinding recursive calls. But now I've finished the recursion, and I'm outside of it again. I'm going back to the function that called me. So I can return the value 6. And then look at whatever return address I've got stashed there to know where I go next. Okay, so what does all this mean? Well, what you should think in your what you should be sort of thinking in your head now is like you have like an idea about why I can say that stack frames are sort of like organized, and what it means to say that things don't exist after your function has been executed. So once we return from sum, we've unrolled the stack. Like these values here just disappear at the point at which we return from the function. They exist no more. And that memory can get reused for other things. But it also saves us from like accidentally leaking stuff, because it always gets disappeared again when the function returns. So what I want you to have in your heads is this idea about what the life cycle of something is on the stack, when it gets like created, and then when it gets freed again. When you start doing operating systems and the C and C++ course next year, you'll see more instances of how this sort of stack rolls and unrolls. For the purposes of object-oriented programming, it doesn't matter what the stack does, like that's nothing to do with objects, but I want you to know about it just from the viewpoint of being able to understand references in Java and pointers and that sort of stuff. All right, let's go back to the handout. So how does this work in Java? So in Java, it's not like C++. You can't choose where things go. In Java, all primitive types go on the stack. So int, bool, char, float, double, all those things that were primitive types, they always go on the stack. Oh, mostly. They mostly go on the stack, and then everything else goes on the heap. And I'll show you an example when they're not on the stack in a minute. So if you allocate an object like a list, or if you allocate an object like an array, or you allocate an object like a string, then all of these things go on the heap in Java world. And you don't get to choose that. That's just how it happens. So let me show you what this means. So here's a program. I've got an int I equals 3, and then I've got an int array containing numbers 1 and 2, and then I've got a string s containing the letter A. So if you look at the stack frame from the top, you can see that there's a row for I, and it contains the number 3. Right? I is a primitive type. I can just store it on the stack. The next row is the result of trying to allocate that array. And so what Java has done is it's gone to the heap, and it said, I need a new array. And with Java, you get extra stuff as well as the contents of the array, which I've just called array stuff. And then you also get the elements of the array. So these primitive types, 1 and 2, they're also primitive ints, but they are on the heap. But they're wrapped in an object. They're wrapped in this array. And you can see that A is nothing more than the address of that array in memory. What have I already shown you today, which is nothing more than the address of something else in memory? A pointer. Great. So we just saw pointers in C and C++. We've seen something in Java, which is the address of something else in memory. In Java, they are called references. And they are slightly different from pointers, and that's the purpose of this lecture. But they are just an address of something in memory. So they're the address of the thing. That is a Java reference. Then this string s, well, string is also an object. And the big clue in Java is that anything that starts with a capital letter is probably a class and not a primitive type. So string is a class. And the string A is like an automatically created object for us that the compiler's done. So it's allocated space on the heap to hold the contents of the string. And it's also allocated space on the heap for all the other voodoo stuff that string objects need, which I might explain later in the course if we have time. And then it's stored the address of that on the heap, on the stack for us to use. So A and S are references to objects which are stored on the heap. And I is a primitive type which is stored on the stack. Now, in C++, if you put something on the heap, it's your job to get it back again and free it later. Java does that for you automatically with something called garbage collection. So like Java goes around from time to time, looks at all the stuff on the heap, says, oh, you're not using these things. I'm going to free them up and other people can use them. So A and S are references. So that's very much like pointers, but you can't do arithmetic on them. So they are not pointers in the C and C++ sense. They are like a very restricted form of what a pointer is. But underneath, in memory, all they are the address of the object that you're pointing to. When I say s.to uppercase, right, what I'm doing is I'm saying I've got some reference s, and I'd like to call this method on the object that it points to. So I'm dereferencing the S, like I'm following that edge on my graph. There's my S up here. I'm following that edge down to the heap, finding the string, and then I'm calling the method on the string. So dot in Java means dereference. It means like follow the reference to whatever it points to, and then do the next thing on that reference. Okay, so if I'm like the world's luckiest lecturer, you're all sitting here now going, everything makes so much sense. If I'm not, then please go and watch the video and like a few times, and hopefully it will become clearer when you can watch it at your own pace. But we've written like s.stuff or stuff.stuff loads and loads of times already in this course. Hopefully now, like it's starting to, like the pieces are starting to come together about what that dot is doing and why it's there and what it sort of means to Java. Now, unfortunately, there's another language called C++ which also has references in it. And a reference in C++ is nothing at all the same as a reference in Java. So about the only thing they've got in common is that they're both called references. But a Java reference is much more like a pointer than a C++ reference. Let me just show you what I mean by that with a C++ program. So here's my stack frame. We're in C++ again. I've allocated I as 3. I've said that k is the address of I, so k is a pointer. And you can see that in memory, k is holding an address. Now, references in C++, you just write them with this ampersand on the left. Don't worry about the syntax of C and C++. If you're doing Chomsky, you'll see it all again in 1b. For the moment, just trust me that line 4 creates a reference to I called j. And if you watch very carefully, in the top right-hand corner of the slide, you'll see the change. So no extra space goes on the stack, right? J does not occupy anything. J is just like another label for I. So there's no value stored with J. J is actually just another name for the same thing. Now, before anyone in this room who writes C++ compilers gets angry with me, that's not quite how they're done, but that's like the semantics of it. So if you imagine that how a reference in C++ works is like an extra label for the same thing on the stack, you won't get confused about what you can and can't do with a reference in C and C++. And I'll give you a few examples of that in a second. Okay, so let me just recap for Java. Primitive types on the stack. Int, long, double, float. When you say int I equals 4, it goes on the stack. Everything else on the heap. If you write the word new, it's an object, you've allocated it, it's gone on the heap. References are values on the stack that point to somewhere on the heap, and I've crazy quoted the point because that's not a pointer. C has already stolen the word pointer and used it for something else, so a reference is a value on a stack that points to somewhere on the heap. References are a bit like C and C++ pointers, but you can't do arithmetic on them. You don't have the full generality of what a pointer is. When they wrote Java, they decided that they wanted to do that. They looked at C and C++ and they went, we don't want to allow people to do that kind of thing. It's really clever, it's really cool, but it also creates lots of problems. We're going to decide not to allow it. And don't get confused between Java references and C++ references. They're really quite different concepts and they work in very different ways. All right. Returning to the handout that's in front of you. So pointers in the C and C++ world and references in Java have some things in common and some things different. So both pointers and references can have no value in them, right? Remember that they're just a pointer is just like a space on the stack, which is an address of somewhere else. Well, that could be an address to nowhere, right? That doesn't have to point somewhere sensible. It could point to nowhere. And so in the C and C++ world, the convention is that if your address is 0, that means null. In Java, null is actually something the compiler understands, and you might see string s equals null, for example. That is a reference which is unassigned. It doesn't point to any objects. Pointers and references can both be assigned to an established object. So you've often seen me write code where I've done string s equals something or other, and then string t equals s. Right? So now I have two references pointing at the same thing. That's allowed, and you can do the same with pointers. Pointers can be assigned to an arbitrary chunk of memory, right? I can just take anything and say, I want to point to that. You can imagine that this is the route to writing really, really, really clever code, and also the route to writing really, really complicated, difficult code that probably has bugs in. In Java, you can't assign a reference to an arbitrary piece of memory. You have to assign it to either a new object of the right type, or you have to assign it to another reference of the right type. You can't just sort of arbitrarily go, look at this memory, I want it to be a long. Pointers cannot be tested for validity, right? So if I look at a pointer, I can't tell whether the address that that pointer points to is actually a valid object that I'm supposed to use, or it's just some random garbage that just happens to be in memory. So the C++ standard doesn't define any way to test a pointer for validity. You might choose in your program to say that I'll always assign pointers to 0 if they're not valid for anything, but that's like up to you as a programmer. You can't like make that guarantee from the language. Whereas with Java, your pointer either points to null, so you can say if x equals null, therefore it points to nothing, or it points to an object of the right type. So that you get promises from the compiler that if your pointer is not null, it does point to a valid object, one that you can use that won't cause your program to crash. And then finally, you can do arithmetic on pointers. So I can say, I've got a pointer to an int, please add 1 to it. I want to point to another int, which is in like one space further in memory. You can't do that in Java. Once you've got a reference and it points to something, all you can do is assign it to another reference. Pointer arithmetic is used a lot in C because people like to have arrays, and they put like all of the elements like one after the other, and then you can go like +1, +1, +1, +1, and like iterate through all of the elements of your array. You just can't do that in Java. So let me just show you some examples of what that means. So I can declare an unassigned pointer by saying some class ref equals null. So ref is the name of the variable I want to hold the reference, and I've just said this has the value null. And null is a special word in Java that just means like an unassigned reference. So that's explicitly unassigned. If you write some class ref2 and you don't write anything, then it's like implicitly going to point to null. Do you remember when I talked about fields in an object, and I said if you don't assign a value to it, it gets the 0 value for the type? So if you have an int and you don't assign a value, it starts off as 0. Java guarantees that if you don't assign a value to a reference, it will be null. C and C++ don't make that promise. Then you can assign to a reference. So I can either create a new class, like a new object here, which is an instance of class ref, and I can assign that to my reference. So ref is now a value on the stack, which is an address which points to a location on the heap where this class ref object lives. Or I can reassign to something else. So I've got the same reference here, and I've assigned it to another object. So that line there has created another instance of class ref on the heap, and it's updated ref to point to the new one rather than the old one. And similarly, I can assign a new reference to point to the old one. So this has created another value on the stack called ref2, which points to the same place that ref1 does. Right. We have got nearly 15 minutes left. I'm going to see how much of that you have all understood. Where are we going? All right, go here. I need to find the results page for this. I'll be